Hi everybody. So in this video, we're going to look at finding the critical region of a binomial distribution. So we'll work through a couple of examples and then we'll try some exam style questions. And if you want to work along with me, you can download a copy of this PDF from my website. I'll leave a link below. So if we begin with this example, we're told that a single observation is taken from a binomial distribution, and the observation is used to test that the null hypothesis is that the probability of success is 0.45 against the alternative hypothesis H1 that the probability is less than 0.45. And for part A, using a 5% level of significance, we've been asked to find the critical region for this test. So if we begin by drawing the binomial distribution, we'll get a curve that looks like this, where the peak is at the expected value, which is n times p, over 10 multiplied by the 0.45. So the expected value will be at 4.5. And then because we're looking at the alternative hypothesis being less than 0.45, this is a one-tailed test to the left of the expected value. So we're trying to find this value of x here, which we'll call c. Now, because we're looking at a 5% level of significance, that tells you that the probability underneath this critical region will have a sum of 0.05. So what we need to find is the value of x that separates the critical region, this region, where we reject HR, to the other region where we accept HR. So if our value of x falls on this side, we accept HR. If it falls on this side, we reject HR. So we need to find this value of x, which we're calling c. And we want the probability of x to be less than or equal to c to be less than the 0.05. Because if it is less than a 0.05, we fall in this critical region. And this is where we can use the tables in our formula booklet. So we've got 10 trials. This 10 is given here. And a probability of 0.45, which is given here. And each of these are the cumulative probabilities. And what we want to identify is the first cumulative probability to be above the 5%, which is this one here. This is at 9.96%. So our critical value then would be the one before it, which is when x would equal 1. Or in this case, we've called this c. So the probability of x being less than or equal to 1 will equal 0.0233. So just over 2%. If we go to x being less than or equal to 2, we go above the 5% and we're in our accepted region. So I'll label this one on the sketch. We'll label this here. So the critical region where we reject HR is when x is less than or equal to 1. Okay? And then for part B, state the actual significance level of this test. Well, this is given by this probability. Because we have a discrete random variable, the next value that x could be is 2, and this is the 9.96%. So the actual level of significance will be 0.0233 to 4 dp. Okay? Let's try another question. So in this question, we're told that a random variable x follows a binomial distribution with n equals 12 and probability p. A hypothesis test is conducted so that HO p equals 0.4 and H1 p is greater than 0.4. For part A, find the critical region of the test at 5% level of significance. So again, the first thing I'm going to do is sketch this distribution. And now because we're looking at p being greater than 0.4, we're looking to the right side of the expected value. So we'll call this value C. And again, this expected value will be the number of trials multiplied by the probability. So this will be 4.8. And we're given a 5% level of significance. So that will be the area to the right of this critical value, 0.05. So we need to find the probability of x being greater than or equal to the critical value, which needs to be less than the significance level, 0.05. Now it's worth remembering here that the tables are all cumulative, which means that they find the probability coming from the left towards the right. So we've got n equals 12 and a probability of 0.4. So we're looking at this column. And if this would be the 100%, then we're looking at 0.95%. And then if we go down these probabilities and we're looking at the first one to go above the 0.95, which is this one. And this is when x is less than or equal to 8. So a probability of x being less than or equal to 8 will be equal to 0.9847. But because we want the probability of x being greater than our critical value, we need to consider the probability of x being greater than or equal to 9. And this will be 1 minus it being less than or equal to 8. So 1 minus the 0.9847. We can work this out and we get 0.0153. Okay? So our critical region then is that x is greater than or equal to 9. As soon as it's 9 or above, we fall in this critical region and we reject HR. So the actual level of significance will be in this probability here, 0.0153. And then for part C, a sample is taken and the observed value is 9. Based on this observation, state the conclusion of the test. So we'll say that because x is equal to 9, this falls inside the critical region, and therefore we reject HR. Okay? Let's try some exam style questions. So in this question, we're told that a pharmaceutical company is testing a new drug for a disease. They will continue development if the proportion of patients who show substantial improvement after treatment is greater than 0.7. A test is conducted at a 5% level of significance using a random sample of 14 patients. We've been asked to identify the critical region for the test. So for this question, because we've been given a probability of 0.7, which isn't in our tables, and 14 patients, I'm going to show you how to do this using a calculator rather than the tables. If we say that x is distributed binomially with 14 trials and a probability of 0.7, where x is the random variable, the number of patients who show substantial improvement, I'll work out the expected value of x as n times p, and this will give us 14 times 0.7, or 9.8. Now I'll sketch the distribution. I'll label the 9.8, and because we're looking at greater than 0.7, this is our alternate hypothesis, we're looking at the region to the right. Again, this is a one-tailed test. I'll label this as C. At this point, I also need to state my hypothesis. HO is that P is equal to 0.7, and H1, the alternate hypothesis, is that P is greater than 0.7. So what we need is the probability of x to be greater than or equal to C, to be less than our significance level of 0.05. I'll label this on a diagram. So to show you this on a calculator, if we go to Home and Distribution, we want Binomial CD, and now we're going to choose List. Now for x, I'm going to choose the values 9, 10, 11, 12, and 13. So I'm just recreating that table which is in my formula booklet. We'll execute that. We've got 14 trials and a probability of 0.7. We'll execute this. Then if we go down in our tables, we want the first probability to be above 0.95, which is when x is less than or equal to 12. So we'll say that the probability of x being less than or equal to 12 is equal to 0.9525, okay? And again, because our critical region is when x is greater than or equal to c, we need the probability of x to be greater than or equal to 13, which is 1 minus the 12. So this will be 1 minus the 0.9525, which gives us 0.0475, okay? So the critical region is when x is greater than or equal to 13. For part B, the actual level of significance, this will be the 0.0475. And then for part C, given that 12 out of 14 patients in the sample show substantial improvement, perform the test. Well, if x equals 12, and this is when c equals 13, then the 12 would fall in our accepted region. So we'll say when x equals 12, accept HO as 12 lies outside of a critical region. Therefore, a significant proportion do not show significant improvement after the treatment. Okay? Let's try our final question. So for this question, we're told that a company claims that 35% of its peas germinate, and Joanne tests this by planting 15 peas and recording how many germinate. Then for part A, we've been asked to state the null and alternative hypothesis for a two-tailed test of this claim. The two-tailed test means that the probability can be greater or less than what it's claimed to be. And then at 5% level of significance, determine the critical region for the test. For part B, state the actual significance level. And then for part C, given that 8 out of the 15 germinate, decide whether this supports the company's claim. So do you want to try this question yourself? You can pause the video and come back when you're ready. Okay, so welcome back if you had a go. So I'm going to perform this using a calculator rather than with distribution tables. Our hypothesis is that HO is that P equals 0.35 and H1, P is not equal to 0.35. So we haven't been told in the question whether we're testing if P is less than or above. So because of that, we have to test both. Then if we define our random variable, we'll say that X is distributed binomially with 15 trials and a probability of success 0.35, where X is the random variable, the number of peas which germinate. And then I'm going to sketch its distribution. And the expected value will be 15 times 0.35, which is 5.25. And then because it's a two-tailed test, we're looking at the regions to the left, I'll call this C1, and the region to the right, which I'll call C2. And each of these regions have a probability that is half the significance level. So this will have a probability of 0.025, and so will this. So if we go to our calculators, we'll choose distribution again, binomial CD, list, and I'll begin by trying to find C1. So I'll enter 0, 1, 2, 3, 4, and 5. A number of trials 15, and a probability of success 0.35. and we want the first probability to go above the 2.5%, which is when x equals 2. So our critical region, probability of x being less than or equal to C1, which is less than the 2.5%, so x will be less than or equal to 1. Because as soon as we go above the 1, which is 1.4%, we go into the accepted region, okay? And it's worth noting here that probability, which is 0.0141, because we'll need that later. Then to find C2, if we go back to our list, we'll start at 8, 9, 10, 11. We'll try these. Same number of trials, same probability. And we want the first one to go above 0.975, which is when x is less than or equal to 9. So if the probability of x being less than or equal to 9 is equal to 0.9875, then the probability of x being greater than or equal to 10 will be 1 minus this. And this is 0.0125. So if I mark each of these critical values on our distribution, we've got less than or equal to 1 and greater than or equal to 10. So the critical region is when x is less than or equal to 1 or when x is greater than or equal to 10. Okay? And then to find the actual level of significance, we need to find the sum of these probabilities. So we'll add each of these together, the 0.0141 plus 0.0125, and this will give us 0.0266. And this will be our actual level of significance. And then for part C, Joanne observed that 8 out of 15 peas germinate. Decide whether it supports the company's claim. Well, you can see the 8 falls between the 1 and the 10. And this is in our accepted region. So we'll say, since x equals 8 falls outside of the critical region, therefore we'll accept HR. Joanne's claim that 35% of peas germinate is correct. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson and a PDF that accompanies this video from my website, mrmathematics.com. I'll leave a link below.